Hey, today the topic is the second fundamental theorem of calculus. This corresponds with section 5.4 in our textbook. So what we looked at last section was the first fundamental theorem of calculus, where you took the general antiderivative, so you got big f of x, and then you did the upper bound minus the lower bound. So big f of b minus big F of A, and the C's would cancel out naturally. Now the second fundamental theorem of calculus. The second fundamental theorem of calculus takes the first fundamental, which we saw last section. You have the upper lower bound A and B, and then those upper and lower bounds, one or both, can be replaced with a function. The function could be as simple as x, or could be something more complicated like 10x to the third. And that could be your upper, your lower, or both upper and lower bounds. Also, you'll see in the green highlighted circle, there's f of t dt versus f of x dx, and then in the green, big f of x equals. So let's kind of look at this in practice, how it happens, and we'll develop a pretty nice shortcut for the process, okay? The first step of the shortcut is you're going to skip example 6, okay? Now the second fundamental theorem of calculus, the actual theorem, states when you take the derivative of an integral defined function. The derivative and the integral end of the word is antiderivative, so inverse, derivative, antiderivative. They cancel out, leaving with only fx. So just your upper bound, which is function defined. So let's look how that happens, okay? So let's kind of work through an example or two, kind of see it happen in action, okay? So we have ddx and we're going to evaluate our antiderivative, so our general integral. So t squared becomes 1/3 t cubed. T becomes, 1 becomes t. And evaluating from x to 0. So now let's go ahead and evaluate. So plug in x, subtract, plug in 0. So 1/3 x to the third plus x, and there's the upper bound, minus the lower bound, 1/3 0 cubed plus 0. Now all those zeros cancel out, so we just have the derivative of 1/3 x cubed plus x. The derivative of that is 1/3 times 3, just 1, so x squared plus derivative of x is 1. And hey, how nice, got our original answer. See how the t's just got replaced with x's? So when you have lower bound as a constant, upper bound as an x function, just x, simple replacement. Let's look again over here. So now from 2 to x. So 2 still a constant, more interesting than 0, but still just a number. Upper bound, a function, a really basic function, x. So ddx antiderivative of 5t is 5 halves t squared minus 3t. Going to evaluate from 2 to x. So now we'll go ahead and plug in upper and lower bounds. So 5 halves x squared minus 3 times x. There's the upper bound, so x plugged in. Now minus the lower bound. So 5 halves and 2 squared minus 3 times 2. Close the bracket. And now take the derivative of all this. Well, the derivative of a number cancels out. So your lower bound, when you plug in 2, those all cancel. Derivative of what I have left over, so 5 halves x squared. It's just 5x. Derivative of minus 3x. It's just minus 3. So hey, look at that. We have the 5t minus 3, the 5x minus 3, and just the t got replaced with the x. So when your lower bound is a constant, upper bound is just x. Simple replacement, okay? So of course, let's make it a little more complicated. If our upper bound is a function, but a 5x squared, a little more. So let's go ahead and do the general antiderivative. So t becomes 1/2 t squared. 1 becomes t, evaluating from 0 to 5x squared. So let's go ahead and walk through that. So dx, gonna plug in upper and lower bounds, subtract them. So bracket 1/2 of 5x squared plus 5x squared. Did I do that right? So the t's replaced with 5x squared. I think I'm good, okay. So now replace the t's with 0. So 1/2 0 squared plus 0. Well, of course, being OCD, what color did I use? I used blue, okay. Does it matter? Really? No. But in this moment, I think it matters, yes. So blues cancel out. Gonna do a little work in the kind of margins here. I don't want to rewrite the whole line, so 5x squared, that's 25x to the 4th, so 25x to the 4th over 2. 5x squared is 5x squared, so take the derivative of this, so 25x to the 4th over 2, so take the derivative, so 25x to the 4th, so bring the 4 down, that's 100 over 2, so 50. X to the 4th is now x cubed plus 10x. Now that answer, 50x cubed plus 10x, kinda different than what we started with at t plus 1. Now get ready for the math magic, okay? Let's factor out a 10x. Leave us with 5x squared plus 1. So take a look at what I started with. Our integrand, the t plus 1, and the upper lower bounds, and what they end with. And try and see if you can make any connection. The t plus 1, now 5x squared plus 1. The upper bound, 5x squared, now we have 10x. So when your lower bound, or any really, if your upper, lower bound, or both are functions, there is a shortcut you can do. You can do this work like you have, of course. You can do that. You can also remember a shortcut, okay? You have your integrand, t plus 1, changed into 5x squared plus 1. Outside you have 10x, which is the derivative of 5x squared. So let's go right here for a shortcut. This is when your upper, lower, or both bounds are a function more complicated than just x. So plug in the upper bound to the integrand, then multiply by the derivative of your upper bound. So do that, plug in your upper bound to the integrand, then multiply by the derivative of your bound, and then repeat that. With your lower bound. And then, of course, this is still the fundamental theorem of calculus. Then you subtract the two. Alright, so there's kind of your shortcut. You can, of course, do the work like I did in the 7a, 7b, and 7c, or 8a. But if you can remember the shortcut, do that, okay? So example 8b, take a look at that, try it out, check my notes. Example 9, look at that, then also check my complete notes online.